Hi, my name is David Hart. I'm a hydrogeologist at the Wisconsin Geological and Natural History Survey. Today I'm going to talk about low cost and easy instrumentation for groundwater surface water measurements. There's a huge cast of characters that supported this work. It's representative of several years of projects cutting across different locations across Wisconsin. Beloit College, Sue Swanson, Jay Swestrick, UW-Madison in Geological Engineering, Chen Wu, Ben Sarin, Dante Frada, Susie Richmond in Geosciences, Catherine Christensen, Gene Barr, Mike Cardiff, and then USGS, Andy Leaf, and then also the DNR, Kirk Olson. So this is really kind of driven by decisions concerning our natural resources. We're doing more and more complex modeling, and that relies on data. So for example, if we're going to do some ecological limits of hydrologic alteration, if we're going to try to figure out what happens if we get more recharge or we are stressing some water body by pumping, we may set up a groundwater flow model, and then we may couple that groundwater flow model with steam temperatures, and those are going to help us understand how we may affect some wildlife, perhaps some fish here, perhaps a trout, something like that. So we're looking at model. Those complex models require more and better data to constrain them. I've got 3 books here, and each one has a Wisconsin author. Applied groundwater modeling has Hunt and Anderson. Discrete signals and inverse problems, Dante Frada. Parameter estimation and inverse problems has Cliff Thurber. So there's been a lot of work done on the modeling side. So here I've got the basic equation for doing inversions, where you have data is equal to some model operating on some set of parameters. And so there's a ton of stuff done on the modeling and parameterization side. I think the groundwater side needs to keep up a little bit. I think the modeling's gotten ahead of us a little bit. Let's see if we can come up with some ways to improve support for models. What I'm going to talk about today, one of the things we can do is we can use temperature. It's an easy measurement and is common. The variations are found throughout nature, and so let's see if we can use it. Mary Anderson has a nice review paper. He does a groundwater tracer. That's a great starting point if you're thinking about using temperature. But we're going to, in the examples today, I'm going to use it for identifying groundwater discharge areas in streams, and then also we're going to look at using temperature to measure seepage. So this response that we're going to use to use temperature and create more data to support our models, to support our understanding of groundwater surface water interactions, makes use of some trends. The first one is locating data is now easy. There we have GPS on our phones. We can put GPS all over the place. It's costs next to nothing. It used to be very difficult to locate yourself in the world within several feet. Now it's trivial. Storing large amounts of data is low cost. 10,000 text lines of data is trivial, especially if you can barely find that on a 32 gigabyte card, micro SD card. And in fact, it's kind of nice to have one of these adapters, because these little cards are too small. Sometimes they're almost too small and easy to lose. And the other thing was we can develop prototype instrumentation. We've got low-cost microcontrollers for $30 or so, wide range of sensors, and then we've also got these internet project hubs, groups of users who are building and things and putting it on the internet with instructions on how to use it. It's part of, I think, a broader trend that I think that we've kind of lost a little bit in the last year or two, but I fully expect it to come back. And this maker culture where where it combines do-it-yourself hackers and artisan cultures. And so it's all kind of comes together, and it's this cut and a paste approach to standardized hobby technologists. And one of the outgrowths of this are a thing called maker spaces. And I just Googled maker spaces near me. And I found UW-Madison Makerspace, the Badgery, and Sector 67. And these are just like clubs or places where you can go where there may be a metal or wood lathe. There's all sorts of tools there. There's expertise on how to use things. There's soldering irons, just kind of support for people who want to build things themselves. Here's one of my favorite examples. The Badgery was one of those maker spaces that you saw up there. And you can see this, here's a list of the tools: woodworking, welding, blacksmithing, sewing, 3D printing. You know, for a few dollars a month, you have access to all of this. And so that we can build things. And this young fellow here built himself an electric longboard. And he didn't want to spend thousands of dollars, but the one he built can go about 7 miles and up to 26 miles per hour on a single charge. And you can see he seems to be moving rather fast if you're looking at the background there. So let's just kind of look at doing this. Let's Google Arduino, which is one of these microcontrollers, and temperature. And so we've got a nice page here that this fellow set up on the Arduino. So Arduino thermometer with DS18B20 temperature sensors. So this page kind of does it most of the hard work for us. It says what materials are needed, how to connect the sensors. It provides a working diagram and a program, or what they call a sketch. And if you Google this, you can see we could have gone with thermocouples or thermistors. There's a lot of different ways to measure temperature. For what we decided to do here, we went with this sensor because it's accurate, waterproof, easy to install, and you can connect a lot of them just on a single port. So you don't have to, they're really quite easy to plug into what we would want. If you Google Arduino and GPS, you come up with a nice little shield which you just plugs in on top of your controller. Your microcontroller is here at the bottom, and then the shield plugs in on top. And so the shield, it consists of a slot for an SD card. Here's your GPS antenna, and here's a little keep alive battery. And then you can do some soldering connections here if you want to do some external wiring. There's multiple boards that we could have used to do this. I went with a company called Adafruit, and because I found their stuff to be pretty easy to implement, and the cost. Again, the cost of the microcontroller and the board together is about $50. So we're not looking at having to spend very much. The accuracy of the GPS I've found to be significantly better than my iPhone, like a decent a recreational grade GPS unit that Garmin that you might have for hiking. And so we put all this together in a little orange box here. It's got a couple of those temperature sensors. It's also got the GPS inside of it here. And here we're recording stream temperatures. And here's Catherine Christensen recording temperatures with an old-fashioned temperature recorder. Here's Professor Gene Barr. We're up in the Marengo River area in northern Wisconsin, trying to figure out where the trout may or may not be, and relating that potentially with temperatures. But this box is running right now, and it's recording its location and it's recording temperature. And what we record are time, latitude, longitude, every second or two. And a couple AA batteries will run this thing for hours. Kirk Olson at the Wisconsin DNR had seen a presentation I had given, and asked if he could perhaps use this for some of his own work down in southwest and western Wisconsin. And so I shipped it off to him, and here's some results from Mapledale Creek, some of the temperatures. Dark green is cooler, lighter green is warmer, and then he's also got the density of brown, or the relative number of brook and a brown trout here. So brown is brown and green is brook trout. You can see those densities there. You can see the upper part of the Mapledale Creek is cooler. We have another tributary coming in here. This tributary is significantly warmer. Then you can also see a couple other cool spots here and cool spots here. Those are associated with some springs. So just by walking or floating this creek, Kirk was able to identify some the differences between the creek and its tributary, and then also was able to identify some locations where there might be some cooler water coming in, and those might be refugia for the trout when things got a little bit warmer. Here's another example that Kirk collected from the La Crosse River up by Sparta. Here's a to the north here is a reservoir, and then we have another one down to the south here. And again, the color reflects the temperature. Here's the data, and we start off at about 15 C up in the north, and as we go down to the south, we're in this lower reservoir, we're up to 18 degrees C, and that's not over, it's over a pretty short range. If we zoom into this area here, we can see again a couple springs where the water is considerably cooler, several degrees C cooler coming in here. There's probably another spring coming in here, and another spring potentially coming in here. So again, we can see kind of the finer structure, the finer scale temperature variation within this river that it would be very difficult to do if we had a pencil and paper and we're just writing things down. This thing's recording continuously, so as long as we keep the sensor in the water, we can kind of check things out. We can also like move the sensor around and see, you know, is that deeper pool, what's the temperature in that deeper pool versus this seepage area? How are things varying within the stream? We can immediately get that spatial variation, and it's located for us in both time also and in space. So the other thing, you know, this seemed to work pretty well. So what we thought is, let's extend the Arduino to doing some water chemistry instrumentation. So again, we included our GPS. You can see there's the antenna. Again, it's a different board, but it's the same sort of thing, where we have a slot for a card, and then also a keep alive clock. We had to use a bigger, we couldn't use the regular Arduino. We went with Mega here, and so it just has a little bit more capabilities. But again, low cost, similar, the sketches are pretty much the same. And then we connected a pH, nitrate chloride, conductivity, dissolved oxygen. Here with temperature, we used thermocouples rather than those digital, those DS18B20. And the reason was there's less thermal mass here, and so it could change more quickly. We also connected a turbidity sensor. This sensor, this is the sensor here. These are used actually in your dishwasher and your clothes washing machine, because so they know how clean the water is. Kevin Fermanak at UW Green Bay had a student calibrate one of these, and they actually do quite a good job. And I would, if you look for Kevin Fermanak, Google him, and you can see the work that he and his student did looking at turbidity in a stream following some storms. Really pretty nice work. But this is also an option to connect again. Oh, and I should just say the cost for all of that was about $1,000. So we here's kind of the setup. Each these individual pieces here are kind of signal conditioners for the Arduino sitting here, and then here's the GPS. So things are all connected together. Here's all the input plugs you can see for the box. We settled on Pelican Brief boxes after looking at some other enclosures. These are waterproof, they're rugged, and the plastic's really quite easy to work, and so that we've kind of settled on Pelican boxes. Here we went with a flow-through cell here, and you may wonder, why did we split this thing into three different compartments here? So we'd have inlet here, it would come out the top and then go into an inlet here, come out the top, out the back, and come into an inlet here. Why do we have three compartments? Well, the electrical conductivity and the nitrate and the chloride probes would all interact with each other. They all use an electrical voltage, or they're sensitive to an electrical voltage, and so we had to separate them. And we then so we separated them with the tubing, and then we also ran the tubing through a grounded brass tube. So a flexible tubing would come out, go through a grounded brass tube, and then would connect them. So we kind of electrically separated them as well too. So that's why the three we have here, and that's why we also one of the reasons why we went with a flow-through cell, because we can't just dip these things into water or they're going to interfere with each other. In retrospect here, we were never happy with how the chloride or the nitrate, these are ion-specific probes, we were never really happy with how they performed, and so we probably could have done without them or tried something different. Maureen Muldoon in our office is working with a different style nitrate probe, one that uses looks at wavelengths of light to look at nitrate concentrations, and that might be something that we could incorporate into a system like this. But anyway, there's our system. Here's how we implemented it. We have we kind of went overboard here, where we put all sorts of instrumentation on the canoe. In addition to the Arduino water chemistry, we put GoPro cameras in front, one in back that looked down below. We put a fish finder in so we would know depths. The water inlet, you can see here, is this tube. It's pulling water from about 10 centimeters below the surface. It goes through a peristaltic pump, and then it goes through our flow-through cell. You can see some of the probes here, and electronics tucked under the front seat, and then it is discharged out the canoe, the other side of the canoe. We also connected an EM31 ground conductivity meter. Again, that was located. And this system, I think it requires a pretty steep learning curve. Catherine Christensen here mastered this instrumentation, and toward the end of her degree was able to routinely get high quality data. Susie Richmond here designed most of the electronics that are running both recording the EM31 location and time, again Arduino GPS, and that's recording the location and timing for this chemistry data. But it's a complicated system. There were 7 batteries that we'd go out for 2 hours that you didn't want to have fail. An example of this then is we went to the McWanago watershed in southwest or southeast Wisconsin down here. It's a nice pretty stream and creek. Here's what it looks like. Here's the McWanago River. Here we're upstream. Here's a spring pool found way upstream. And so here's that same spring pool. Let's see if we can get there's some nice beautiful little spring boils in there. You can see the temperature starts out cool around 11, 12 degrees C, and then warms up as we go downstream here. So the temperature, as you'd expect, is cool. We're doing this in the summer, and then warms up. And there's where that spring boil is. The specific conductance starts off high and then begins to decrease. It increases a little bit as we go past this tributary here, this connection here, but then it starts to drop again. Again, coming out of the spring, our pH starts out lower and then increases as we go downstream, becomes more basic. And so, you know, with these three data sets, we have them spatially, we have them temporally. We can then start to put together some thoughts, some hypotheses about how groundwater discharging from a spring pool here, how does this groundwater evolve as it moves downstream and through the system, and what might that mean for the ecology of the system? What species might we expect to find here versus down here where things might be a little bit different? We have a map of the chemistry. Okay, so that's kind of going from the Arduino, locating chemistry. These are more now in situ, in place measurements where we're going to look at seepage. And you know, traditionally, if we're going to look at seepage into a lake, we may put a well off to the farther away from our water body and look at the water table and look at the lake level, and then we can look at what's the gradient toward the lake. And then maybe in the lake bed, we'll put in a lake bed piezometer and we can see if there's groundwater discharging up into the lake bed. And then we also might put in a seepage meter, and where here we would you know, this is often just what we use as a Menard's bucket cutoff, and then with the hole in the top and a valve here perhaps, and we put a plastic bag on there, and we can measure seepage through. So we'll get seepage coming in the bottom. This bottom is open, and we get seepage coming up into here, and then it fills the plastic bag, and that'll give us a seepage rate. However, when we do these seepage meter measurements, they're really highly variable over space. And Don Rosenberry's got some wonderful work. This is probably where I'd recommend anybody start if they're going to be looking at doing any of these seepage measurements. He's thought a lot about it, looked at different ways to handle this variability. Another issue is if we're on a lake and there's a little bit of wind, and we're trying to get a gradient between the lake, a head gradient between the lake and the groundwater here, or the head difference between the lake bottom and the head here. If the lake is, we got waves, we're in a lot of trouble. So it's difficult to see if we've only got maybe a couple centimeters of head difference. It may be difficult. We may have a couple centimeters of waves, and so understanding that differences can be really difficult. So the solutions that we tried first, we would just put in 3 seepage meters, and we'd put a lake bed piezometer in the center, and we'd put seepage meters kind of in a triangle around the piezometer. That we felt a lot better about our results, but more often, very commonly, 2 would show a lot of seepage and 1 wouldn't show any. And what do you do with that? Oh, it's heterogeneous. Well, that's not really all that helpful. Do you average that? Do you throw out 1? You know, it's kind of difficult to know. The other thing, though, that we did is in these places where we had waves at the surface, this was really effective. We just cut the bottom off a trash can, placed it over the piezometer, and made it so that it was just barely into the surface of the lake bed or stream bed, and then but above the lake level here, so it was acted like just a big stilling well. And that was really pretty easy and effective. And so if you're trying to do these lake bed piezometer measurements and you don't have a permanent stilling well around it, just make your own. And so we feel like we can do the lake bed piezometer measurements pretty easily. So now we can get the comparison, the head difference between the head here in our piezometer and the head here right at the lake bed. So the alternative that we looked at using was to do temperature flux measurements. These things have been around now for 10 or so years. And the idea is you put in one of your lake bed piezometers. Again, you get the difference between your lake bed right at the interface here and the head down at some distance below the lake bed here. So here's your head. The head down here is here. The head at the lake bed is here. So we've got our change in head. And you measure several temperatures with depth. We have variation at the surface shown here. And then we have the advection dispersion equation. And if we've got, in this case, we'd have water flowing downward into the lake bed. And so then that would be carrying this signal of heat downward. It would be advecting. We'd have heat transport downward. If we had had the opposite case and the heat transporting upward, we would be pushing or compressing. We'd have only back diffusion of the heat and less advection and no advection downward. So an easy entry into this is to use 1D Temp Pro. It's from the USGS, really pretty reliable and certainly easy to use. For our hardware and our installations, again, we used an Arduino with a clock and SD card slot here. I kind of wish I'd used GPS because that automatically gives you a really high quality time, whereas I wasn't quite as happy with this clock time. But then again, you also need to find the signal. Either way, this worked great. So we're recording time and our data on our SD card. We have 8 D cells rather than the 2 AA cells that we used before, and this will run things for a couple weeks easily. And so here we're going to record 7 temperatures. You can see 1, 2, 3, 4, 5, 6, 7 temperatures. Where we have those sensors taped right at the surface of our PVC here. And so then these all connected. Here's our connectors. These 7 connected here. And then you can see here's an installation where it's hanging off a stake and connected to, here's our pole, our sensors into the stream bed, and here's a stream bed piezometer right beside it so we can get the gradient. And then here's just for your reference, here's an installation of the piezometer. We drive a pipe with a plug on the end, and then we put our Teflon tubing with a screen, a fabric screen, down into the pipe. We pull the pipe, leaving the tube in place, and that's what you see here is the tube in place. So now we can get our head measurements and we can get our temperature measurements. Here's an example from that location. Where here's the variation. This is over from October 28th of last year to November 3rd. So we're looking at nearly a week's worth of data. And here's that time series. Here's the temperature series at 6 degrees Celsius, 10 degrees Celsius. So you can see it was getting cold. We are in October. And so here's the stream bed temperature at 0 meters. Blue is at 1/10 of a meter, yellow 6.16 meters, 0.22, and then the bottom one was 0.27 meters. And you can see this variation at the stream bed propagating into the subsurface here. And so we can, and then we also have our gradient of 0.008, and that's an upward gradient. The flow's coming upward, and we get a flux of 0.69 to 0.67 meters per day over that time period. Pretty constant flux. It varies a little bit, but not very much. And that may seem like a pretty large number, but this was an area of the stream where the flow went from like 2 CFS to 4 CFS in about a mile. So it's an area where there's a huge amount of groundwater discharge into the stream bed. Our And so here's some of the properties we can get. We have fairly high hydraulic conductivity and reasonable thermal conductivities. These are some of the things Temp 1D needs. Last thing, we're nearing the end, is the Kenosha Dunes. We did some seepage face measurements here, where we looked at, here's some erosion. The dune was eroding here. Here used to be the revetment. All that got washed away, and now we're having erosion. And you can see this dark area here is seepage. And here's a close-up of the seepage that you can see there. What we thought is, hey, let's see if we know this is working from a vertical seepage. Let's look at horizontal. And so we just stuck a brass tube into the seepage face. We measured a gradient here. Here's our head. This is the head at the end of the brass tube that's way stuck into the seep. And then we can get a gradient. Here's our head right at the seepage face. And so here's our gradients. Pretty steep, but that's what you'd expect where groundwater is discharging right at a seepage face. So and then we just did another temperature profile where we put our temperature profiler into the seep, and we get again another high but reasonable discharge or flux. And here's that temperature data over several days again. All right, so what's next for our instrumentation is I'd like to pursue this seepage face a little bit farther. We know it's not constant. We know it's going to vary with depth, and it's also probably going to vary with angular direction. So can we maybe tease out the gradients? Can we tease out the fluxes at these seepage faces? And can we do this for all sorts of seeps in all sorts of locations? Maybe, you know, so there's lots of areas where there's kind of distributed seeps. Can we develop instrumentation where we can just put it into the seep and then kind of come up with estimates of flux? And the idea now is to use pressure and temperature sensors rather than just temperature sensors. That gets us out of having to push two things into the ground. We can just push one instrument. And here are some sensors that we're going to start looking at using. This one is using fitness trackers as an altimeter. And so we'll just put a series of 7 or so of these in a string. They'll measure pressure and temperature, and so we can get our gradient and our temperature measurements with depth. And then the other thing we thought, well, let's put a tilt meter on here too, so that we know what angle we're doing this at, and it's recorded automatically. And so we can then use that to calculate our head measurement and really kind of have to spend less time worrying about trying to measure angles. The instrument will do this for us. And again, you can see they're not so expensive. And so with that, I'll see if there's any questions, and I'll acknowledge the funding agencies with the Wisconsin Department of Natural Resources, Wisconsin Department of Ag, Trade and Consumer Protection, Wisconsin Coastal Management Program, and my own organization, Wisconsin Geological and Natural History Survey. And I'll end with a picture of Leola Ditch in November. Thank you.